forward to talking about the development of a teleoperation framework using the hybrid ROV NUI. As Zach mentioned, my name is Allisa Dalpe from Woods Hole Oceanographic, where I am a research engineer. So quick overview. So I'm going to give some background on Woods Hole Oceanographic, or as we call it, WHOI, in the Deep Submergence Lab where I work. I'll give an intro to nearing under ice, which will be the main vehicle focus for this talk, and then talk about the teleoperation framework, some background, and then 2 tech demonstrations that we performed on exploration vessel Nautilus in the past year, and also touch on some of the other objectives, multi-vehicle coordination, and also a research area we call co-exploration. Then I'll get into what's next for NUI. So WHOI has sort of a surprising amount, over 1,000 employees, and we also have about 130 joint program students. We're actually an independent nonprofit, so we have funding from government, academia, NOAA, NSF. So it comes from a large variety of areas. So I guess working on a lot of different types of projects and a lot of variety of science. 5 different research departments. So I'm part of the Applied Ocean Physics and Engineering. There's also biology, geology, marine chemistry, and physical oceanography. So within the Applied Ocean Physics and Engineering department, I'm part of the Deep Submergence Lab, or DSL. So we operate a variety of custom, unique vehicles that go to the deep sea. So a few of them are here. On the left, we have Mesobot. So this is actually a mid-water sampling vehicle, and it follows isolooms and is really a unique and implemented for a specific science goal. We have Orpheus, which is actually a full ocean depth vehicle, 11,000 meters, and built to be relatively low cost and small scale. It's only about 500 pounds, which relative to some of these other vehicles listed here is pretty low weight. Then we have something called the National Deep Submergence Facility, which is within DSL, and this operates Alvin, which is human-occupied, Sentry, which is an autonomous underwater vehicle, and Jason, which is our large-scale remotely operated vehicle. So these 3 are grouped together because they're our most operational vehicles, and they're there to serve science. They're at sea 100+ days a year, and they travel around the world and do what science needs and what they propose. I was on a recent cruise with Alvin, so this is human-occupied with 1 pilot and 2 observers, usually scientists or pilots in training. So every 5 years, this vehicle goes through a complete overhaul. Everything gets unbolted, inspected, replaced. But this was a special overhaul because this was to send it down to 6,500 meters, which is a big certification. They're certified by the Navy, so there's a lot of paperwork and a lot of checks that have to be done to get this certification. So in July, we left Woods Hole and did 500-meter increment dives, getting those certification checks until we reached Puerto Rico off the coast. And we were able to get that 6,500-meter dive, the certification. But this also allowed, because there are sea trials, to do some other engineering work. So this is what I was part of, we did some upgrades to the navigation system. So the old way is using USBL and dead reckoning from several sensors. So the pilots can take both of those inputs and they sort of decide which one they think is correct at that moment, depending on whether they think there's some faults going on with the USBL from the ship or whether the dead reckoning drifts over time. Our new way is we integrated an inertial navigation system. So this uses fiber optic gyro plus fuses some other inputs using a calming filter. So this basically fuses all of the solutions together and gives you the best fit for all of them. So over that cruise, we did the integration of that data pipeline, some new GUI interfaces. So this is NavG, what you're seeing here. And this is used for most of the DSL vehicles in the lab. And there's different plugins and different sort of flavors for each vehicle. And this is our main area for both navigation and situational awareness. So we can see the vehicle, the ship, and any other marks items in the water. So along with that, we also have to train the pilots to use this new software. They have a very standardized way of doing things and how they operate. So to have something new, they want to fully test it, understand it. So over time, we'll remove the USBL and dead reckoning solutions to declutter the screen, but and then they will just have those one INS hits on that screen to navigate from. I was also on a recent cruise with Sentry. This is a 6,000 meter vehicle with 24+ hour endurance. Does a whole variety of biological, chemical sensing. Scientists usually bring their own sensors that we can integrate, pretty flexible payload. We usually are also done with alving, so we'll map all night, give them a brand new map, and then the pilots can navigate based off that brand new map in the area that we're at. Robot operating system is our core software structure, which is open source, and most of our code is actually on Bitbucket, readily available. So this September cruise was specific to looking at sort of application to oil spills and the natural release rate of oil. So we're in the Gulf of Mexico. Conveniently, we left Tampa a few days after or before Hurricane Ian came through. So unfortunately, we lost a few dive days, but we're able to continue the cruise. Some of you may recognize Alex Padilla over there on the left, working hard on the HCF sensor. She was also on the cruise with me, and that she was there as part of the science team, integrating that sort of new payload onto Sentry for this specific cruise. And there's actually 4 of us from UNH. So UNH has been well represented on almost every cruise I've been on, so that's great. Moving to nearing under ice, and this will be the vehicle I will be referencing for the rest of the talk. So this is 5,000 meter rated, built for unique capabilities under ice. So because of this under ice need, it's built to travel 40 kilometers laterally, so horizontally, so that it can travel under ice while the ship cannot move due to not being in the ice pack. So there's onboard batteries. We use fiber optic tether, but it can also be tetherless, which is why it's called a hybrid ROV. And we have a manipulator arm, so we can also do sampling, mapping, camera imaging. So have a whole suite of sensors on there as well. And if you look at the top here, we have doors that open and close, and that's when the arm can do the sampling. So as I mentioned, the hybrid capabilities. So we have a depressor system, which houses our fiber optic tether. It's actually unarmored. So if you look at the picture here, this is the fiber and this is the diameter of human hair. So as you can imagine, it's very thin, very flexible, but surprisingly strong. It can go tens of kilometers, and we usually have no issues with it breaking. And this is the canister that they're housed in. So we have our depressor where one of these canister lives for scale. This is it here, it's about 5 feet tall or so. Then we have a tow body that is deployed from this depressor. This has a second canister to take the strain off of the umbilical, which is sort of a thicker, heavy-duty cable that is attached to the actual vehicle. We also have our main source of communication. If we lose that fiber, we have a 10 kilohertz and 3.5 kilohertz acoustic micromodem. 10 kilohertz we use for more vertical communication, but once we reach sort of those horizontal distances, we move to the 3.5. We've done some recent testing with that and have gotten comms up to about 10 kilometers with the 3.5, which will be great for some work I'll mention later. So moving to the main portion of this talk about the teleoperation framework, I'd also like to recognize my collaborators, Stefano, Mike, and Andy, who are all actively working on this with me. So telepresence has actually existed for a couple of decades at this point, and this has really just focused on bringing scientific expertise from shore to ship or vice versa. So whereas teleoperations is more direct operational actions, so this is actually driving an ROV, manipulating the ROV, actively changing the mission, and doing all these things from shore. So the aerospace industry, it has a lot of experience with low bandwidth environments at really long distances. So there's definitely a lot to learn from them, although we have unique challenges, both in the medium of the ocean, among other challenges, such as changing mediums. And we have at WHOI a lot of customized vehicles that change mission types depending on cruises. So whatever we implement needs to be flexible and sort of platform agnostic as well. So there's also a lot to learn from the telepresence. So like Nautilus and Ocean Exploration Trust, as you may know, they have a huge telepresence development and implementation that they use during their field seasons. So there's a lot to learn there, from video streaming to audio connectivity, among other things. But really, industry is leading the way here for this area. So this top right ship here is a new vessel. This is Armada, which is a company owned by Ocean Infinity. At 78 meters, they want to build 23 of these, which they're supposed to be completely autonomous, but able to deploy ROVs, ASVs, sensors, among other things. So this is sort of what their centralized command center will look like. And they're actively working on this. And I believe they did the sea trials for that ship last spring. So for our vision, we want to, from one or more remote locations, operate a variety of research assets. As I've shown, there's AUVs, ROVs, all the acronyms, using communication links that vary in throughput, latency, loss, and directionality, depending on our connection. Sometimes we use acoustic modems, sometimes they're optical. So we have a lot of different types of communication links that we have to take. So some motivation for this work, there's upcoming regional class research vessels, such as Your Eyes, Narragansett Dawn has a much smaller footprint. So the teams of ROV teams of 10 or more won't necessarily fit on these smaller ships. So being able to downscale personnel offshore will be a huge help. We also have surface vehicles that can act as vehicle tenders. So we have our DRIX that most of you are familiar with here at CCOM, and we've done some work with, which I'll speak to you later. And then also just this push towards the multi-vehicle long duration operations, where it makes sense for people to be operating from shore. They're not actively piloting all the time. There's a lot of mission updates. They care about where it is, but a lot of it can be done from shore. A big thing for us is being able to distribute senior level engineer expertise across multiple assets. So you sort of gain a lot of legacy experience over time of these systems, of these vehicles. So if one of these engineers who have been around all the vehicles and have all that experience can actively operate multiple at the same time, it helps us with staffing. We don't need the senior personnel always out there. It's great for training. It really opens up the pool of operators that we can use. Of course, reducing travel and costs is a big one. Enabling a more diverse workforce, so those who can't go to sea can actively participate in ocean exploration, while being able to produce that larger operational footprint and being able to explore the ocean in a greater volume. So this is the first tech demo I'll speak to. So this was on EV Nautilus September, about a year ago. So here's nearing under ice off of California, not under ice, yes. But it's a great test platform because we have all these different communication links. We can do sampling. There's a lot of sort of test bed things we can do with this vehicle that made it the right choice. So we identified 4 different target areas to start off with as we explored this teleoperation space. The first is real-time engineering and troubleshooting. So this is if you have a problem on deck with the vehicle, it's being able to phone home and get some input and some expertise on how to fix it. And as I'll show, also during live dives. Next is our pre-dive checkouts. So before a dive, we run through a pretty extensive list of items, mechanical checks, software checks, making sure the vehicle is in the state it should be. The third one is remote operations, which is our active mission planning, piloting, anything you do during a dive is classified for number 3. And lastly, we have our data services, which is being able to efficiently package data and move it from shore to ship or vehicle to shore, and vice versa. So our first area, so on this tech demo, we demonstrated we had an optical modem on the vehicle and also on Nautilus's tow sled Argus. So we had what we call the virtual tether. This optical modem could communicate up to 100 meters away. So we did some troubleshooting with some of the engineers who worked directly with the unit on shore. So they were piped into the acoustic, audio link on Nautilus, so we could speak with them freely. They had real-time VPN into our systems, so they could get data, pull logs. Where sort of the old way of doing it is after the dive, you pull the logs, send them to them, they get back to you eventually. Where this was all real time, and they could test things out real time, get real time feedback. And they were able to walk us through some of their troubleshooting steps so that next time we can do it on our own as well. So here is the optical modem seen by the tow sled Argus. So pretty cool. And so Argus, we would dangle above the vehicle. So as long as we're in that sort of 100-meter range, we would get up to 10 megabit per second up and down. Next, for pre-dive checkouts, we deployed some various hardware to help with those, such as cameras. So shoreside personnel would have the situational awareness. Are people around the vehicle? Can I run the thrusters? Is it in a safe state? We have a microphone listening to our acoustic modem so that that data was fed to shore, so that person could check the frequency and the timing to make sure those all check out and it's working correctly. We also have a burn wire tester box. So the burn wires are our emergency release system. So this was hooked onto the vehicle while we were doing our pre-dive, and that data was fed back to shore. So they could check the voltage, current, and make sure those all were within range. For remote operations, we did demonstrate piloting from shore. So with the Xbox controller, Zach over here was operating the vehicle from thousands of miles away. We were seeing latencies of about 1 to 2 seconds, and we have our fiber optic tether connected for that demonstration. Oh, you see him here, and this is his nav G screen, so he sees the ship and both vehicles. And then he could also actively change the mission plan and interact with our vehicle GUI, all from shore. Rich Camilli, who was also taking part in this cruise with his lab, demonstrated autonomous manipulation from shore. So they were able to use speak to text and sort of natural language interface to say, take the sample, and then the arm would move to the designated location and actually take the sample. So we were using different telemetry links for all of this as well. So between the optical, acoustic, and fiber, demonstrating that we can move between these and have our mission planning such that it takes into account these different connections. In terms of data services, we demonstrated here real-time viewing of multi-beam data on shore. This was from the optical link, so wireless. So we processed it first into preliminary maps, and then it was stored into a more memory-efficient octree. And this enabled the more rapid transfer back to the shore of selected regions. So it would move from ship, and then from ship, we would get back to shore in near real time. So then a shoreside operator could say, okay, based on this map, I want to go here. So that active mission sort of change and integrated with shoreside personnel's interests. Our second tech demo, this was off of the coast of Hawaii back in May. So this is just to demonstrate how far away some of our operators were. So we had a software engineer in Woods Hole, our electrical engineer in Florida, and then the rest of us were on the ship out in Hawaii. So here we really focus on the remote engineering aspects of teleoperations. So we tested the viability of Microsoft HoloLens 2 for real-time troubleshooting. So I'll speak to some of what we did there, a demo, and some operational parameters that we defined. I'll then speak to the network infrastructure and some of the items that we pursued there, and then some of the lessons learned and challenges moving forward. So we had this Microsoft HoloLens. So we wanted to use this for troubleshooting. You can send annotations, documents, images. So as you see here, this is a connector pinout that was sent from shore to the headset here. So I could see that in real time and compare it with what I was seeing on deck. And this way we can have that one shoreside engineer actually be able to troubleshoot multiple vehicles at the same time, since they weren't actively working with the vehicle on deck. It's also a great training tool, so you can walk through some common procedures remotely and also learn some of the troubleshooting as you have that senior engineer walking you through these items. So shortly I'll show a demo. We did a CCD test using a serial loopback to demonstrate the viability of this device and to get sort of a frame of reference for whether it's viable for the future. So we had Chris, who's our electrical engineer, and he was to confirm the pinout and test the cable and which test cable to use, and also run through the test procedure. Stefano was the software engineer, so he was navigating the vehicle GUI, which you can see over here and over here, and also to interact with the terminal, so he could power on and off devices from shore actively while we were troubleshooting this device. And then I was on the ship and I was doing the physical connections and sort of acting for this demo as the engineer in training. Hey, Chris and Stefano, we are having trouble with our CCD, so wondering if you guys could help troubleshoot.
Yes.
Yeah, we can.
Chris, could you just point out which connector? Make sure I have the right one.
Sure. Yeah, I see the CTD there. Let me circle connector.
Okay. Yep, I see the green circle.
Okay.
Stefano, can you check if the power's off?
Yeah, power is off.
Great. Connector here. So you want to do a serial loopback test, correct?
Yes, that's what we'd like to do.
Do you have the pinout just so we could check the I have the right serial lines to loop back?
Yes, I'll pull that up here. So if you look at the connector,
yep.
It'll be pins. It'll be the pins with the white and the red wires. Those are the two that need to be shorted together.
Great. So I have those looped back here. So we should be all set. I'll plug it in. Okay, Stefano, you are clear to turn the device on.
Okay, it's powered on.
The serial port, I believe, is 11. So if you could check in terminal, see if we get any characters back.
We have no loop back.
Yeah. So not the great video editing skills. Not really where my expertise lies. But hopefully that at least shows you what an interaction may look like, and just a demonstration of how we may use this in the future. So we definitely saw it was more efficient than troubleshooting via email, which happens a surprising amount on these cruises. So having that real-time feedback and real-time interaction was great. And it's a much better frame of reference for the shoreside engineer versus like a FaceTime call or just a pure audio call to be able to see the system and actually sort of get a feel for that in-person view. So we showed these different capabilities, but a few ongoing questions is what level of knowledge is actually needed for these shipside personnel, and sort of how entry level can you be and utilize this device to bring you up to speed, and what are sort of the potential challenges to this live troubleshooting. I'll speak to a few of those in a moment. So the device currently had no motion compensation. So with a rolling ship, it loses tracking as it uses a lot of gyro and cameras to figure out where it is in space, because these holograms, if I were to walk around the vehicle and come back, those holograms should be in the same spot. So with the motion of the ship, there were some issues there. So sea state 2 was about our limit, although you could still use it for the visual of getting the camera stream back to the shoreside person. So it does still have use in these higher sea states. But Microsoft has recently released a software update where motion compensation has been added. So we look forward to testing that in the future. We were in Hawaii, the device overheated pretty quickly. There's some other models and other devices that have the processor not in the headset, in which case some of that heat would be generated and may give us longer sunlight ability. So about 2 or 3 hours in terms of battery life. And the video resolution was surprisingly good. The shoreside engineers could read cable labels and smaller items, which was great. We found the audio was sufficient for what we needed with the vibration and the sounds of the ship. And we were just connected over Wi-Fi with the EV Nautilus public network, which in terms of research vessels is very good. So we had really no bandwidth issues. We did do some tests with the camera on from my end, and there's some lag, but it was still reasonably usable. Moving to the network infrastructure. So we had 2 links in this case. Our hardware link was a DCB tunnel appliance, 20 megabits per second. So this was pretty much plug and play, so fairly easy setup, but you were limited to working where this device was, so most likely your office. And we also used it to troubleshoot the software VPN, which is our end goal. So we used WireGuard for our software link. It's known as a lightweight open source VPN. And we connected this with a Microsoft cloud host. So this gave us more flexibility of these engineers. They do not necessarily have to be in the office, and also do not need multiple of these hardware devices. We did some data logging. So here, as an example, we used something called OWAMP, which is a one-way ping. And this let us take some data on one-way latencies. And this would better measure the direction of traffic congestion. So we would know that, say, ship to shore is slightly slower than shore to ship. We can design our systems better, knowing some of these criteria and some of these parameters, and moving forward, add some autonomy to actually know and predict what some of these latencies will look like and take actions based on those. We also did a little exploring with monitoring. So with WireGuard, there's an open source event alerting application called Prometheus that we tested along with Grafana, which is an open source data visualizer. So we could get a feel for what some of this network data was looking like and sort of compare that to how we were working operationally and what were those requirements to operate effectively and what connections were actually necessary. But we ran into quite a few firewall issues between the ship and WHOI, so we're not able to fully complete this, but have made some good headway. So some of the lessons learned, time zone is a factor. So our 6 hour, Eastern time is 6 hours ahead. So setting boundaries and sort of those mission call-ups are needed to ensure that the shoreside personnel are prepared to work sort of those off hours or on call. So it's a whole different structure in terms of how we operate that we'll have to think about. We found the audio was an extremely important tool, more so than video. We could deal with laggy video and be okay, but it was really frustrating when our audio was flaky. Another question that we are working towards is the cloud costs. So if we use a software VPN link and end up using the cloud for our data management, how sustainable is this as we increase in scale and size? Again, scaling the number of VPN clients, that can also quickly become complex and lead to other issues. As I mentioned, the firewall issues are coming. So really accounting for security is a big thing moving forward. And by using some of these software VPN links and Microsoft, we can move some of the cybersecurity concerns sort of off to Microsoft and those who are way more experienced with those sorts of issues. And then also lastly, guaranteed connectivity across the research fleet. So Nautilus typically has great internet, but some of the other ships, you never really know how great your speeds are going to be. You may not have that much data per day. So starting to get guaranteed requirements. So for say the UNOS vessels, such as WHOI's Atlantis, starting to figure out what the baseline should be so that we can actually expand on these teleoperation goals. So some next steps. So we should shortly have some follow-on funding to continue this work. And we would like to continue working through this network architecture and figuring out this new CONOP based on some of these lessons learned and what we identified for requirements. And really one of the bigger things for active operations is that network monitor. So we can trigger alerts and have the vehicle in a safe state at all times. So like hold station if we lose connectivity with shore, they're actively piloting, improve some of the audio methods, and again, accounting for that human element and structuring those CONOPs with a more practical workflow. So I'd just like to highlight a couple other objectives from that cruise. So we, as I mentioned a while back, we have this research area called co-exploration. So this is real-time access to survey data over low throughput acoustic links. So during this second tech demo, we demonstrated through an acoustic modem that we had this pre-planned multi-beam survey. We were able to pull up data at 1 meter resolution through this framework. We were able to identify targets from these progressively uploading multi-beam maps. We were able to replan and retask the mission for a photo survey over these interesting targets. And then from there, we were able to pull up images at higher and higher resolution. So you can select a timestamped image. First one usually blurry, but as you pull up more and more of these same images, the resolution gets higher, and you can make out what was here a car that was on the seafloor. And I just also like to point out that Laura Lindsay from UW and Mike Jakuba from WHOI have really spearheaded that effort on this cruise, so I want to recognize them. And then also, you probably recognize a few people over here, Larry and Belle, looking quite pleased with the picture that they saw there because we demonstrated multi-vehicle collaboration. So we were able to use DRIX as that relay from the ship to NUI doing multi-beam mapping. So we were able to successfully transmit a map from NUI through a Summerdyne acoustic modem through DRIX, and as you see here, pulled up on the ship where we could view it. So we also were able to demonstrate this through different acoustic modems, both Summerdyne and WHOI's micromodem. So also we're able to demonstrate that they were modem agnostic and able to move this co-exploration framework across systems. So what's next for NUI? So summer 2023 looks pretty exciting. So we'll be going to Greenland to explore 3 glaciers with lead scientist Dr. Jenny Catania from Texas. We'll be doing a combination of mapping and sampling moraines. So the 3 glaciers we'll be taking a look at is Umi, Rink over here, and then also Conjure, which is shown here. And this is an image of one of these glaciers. We have a second cruise also lined up in the Arctic, leaving from Norway under the guidance of Dr. Chris German, going to the hypothermal vent field of Aurora and the Gackle Ridge. So we'll be on the ROV Polar Star for this cruise, and we'll also be surveying and sampling the vent sites. So NUI will actually be under ice, which it was built for, which is really exciting. So with that, I'm happy to take any questions, and thank you to the NUI team and all of our sponsors and collaborators.
A question about the HoloLens too. When you're using it outside in direct sunlight, did you find that the brightness was sufficient to be able to easily see the content?
I think for the most part, but I was also shielded by one of the doors. I know in direct sunlight, it's definitely, you have to be careful of which direction you're facing.
Was it clear, or because I know that you can also apply like a shading, like a tint to it to kind of reduce the amount of outside light to increase contrast?
Yeah, we didn't play around with the contrast much, so unsure of that. But we weren't able to, because the device is sort of controlled by WHOI. There's some weird like security things where we can't actually customize too much of it. So we're working towards fixing that, but we weren't able to actually like change a lot of the parameters of the device itself yet. Val.
What was your like subjective experience like of using that? Like, did you do it enough more than just the demo to get a sense of whether or not you'd really like to work on the ship while it's moving around with that thing on?
It definitely wasn't bad because of the AR versus VR. So I actually had situational awareness of what was around me. So I didn't feel like I had like any balance issues or just like the thing on my face, but it was hot. But I think it definitely was it was more useful than I actually thought it would be originally. And I found it wasn't, the learning curve was pretty quick, and I got used to it from a couple of those sessions, and I knew the quirks and sort of knew how to place things correctly and that sort of thing.
And then for a quick follow-up question, like what is the user interface for the person who's on shore? Like if, for example, they want to push you a schematic of what you're looking at, like how do they drape that in front of you and figure out where it's going to be and
Yeah, so
the zoom level and all
it's
that?
pretty much a Microsoft Microsoft Teams call. So think of kind of a Zoom interface. And when they push those images, it's sort of a default location that's going to pop up, but like I can move it to wherever. And I can choose to have them follow me around or have them stay in place.
And can you zoom them?
Yes.
Cool.
How do you choose like handheld something?
So it's all sort of hand-based. So it tracks fingers and your hand gestures. So you can sort of pick it up, move it around. It's pretty cool the first time you use it.
Like Minority Report.
Yeah.
Great presentation. So I'm curious with, especially using NUI up in polar regions or where there's extreme cold. How do you think something like this would handle that? If, you have to consider maybe extreme heat, how about extreme cold? But
Yeah, and sort of up there, our other issues is not much satellite coverage. So sort of the internet is much worse as you move to those Arctic regions. But for the cold, I sort of think of having my cell phone while skiing. It usually dies within an hour. So I'm assuming the same would happen. Just the battery life would degrade. Probably still usable for a while, but
You said it had like the NUI also had like an autonomous functionality as well. Is that like in case it loses, in case that umbilical cord breaks, or is
Yes.
it like you would send it out autonomously?
yeah, so there's some sort of basic functions where if it loses connection, it should know like, oh, I was supposed to do this track line, so I'm going to continue on, but sort of acoustically report back with what I'm doing. But we can retask it acoustically. And then there's other fail safes where it's like, if I don't hear from the ship in X amount of minutes, I'm just going to hold station until I hear back. So there's all sorts of like a task tree of like letting it based on sort of communication links of what it does for actions.
Cool. Thank you.
Alyssa, on the optical modem, you said you did 10 megabits per second, right?
Yeah, those up and downlink. So usually we have our uplink higher than our downlink. So
it's
that's,
measured.
yeah, so it's combination.
Okay. And you said it worked out to about 100 meters. What's degradation with distance?
So we were seeing that sort of 10 threshold, I think 40, 50 meters, and then degrade from there. We had it hung pretty consistently, I think at about 40 meters when we were operating.
So at 100 meters per next second? Or
Yeah.
something?
Yeah. And we had quite a bit of turbidity in the water column on one of the dives, so we saw a lot of degradation there. So it also depends on the fairway of the water.
That's why you only want to go to the tropics.
Yes.
You dealt with a lot of different comms. What's your comms of choice? Acoustics, optical?
Thanks. It's not a great answer, is it? Yeah, I think acoustics, as we showed with that co-exploration, there's a lot of development that can still happen, even with that low bandwidth of how we can move data around efficiently. So I think that's what I've worked with mostly, so I'm biased. So I'll say acoustics.
Another question. Despite the fact that you work with WHOI near MIT, mentioned nothing about moose.
Yeah, so NUI uses mostly it's sort of legacy software, whereas Century we have converted to ROS. I'm not sure. I think there's some Remus vehicles that use Moose at WHOI. There's been a pretty big conversion to ROS.
Is it a wraparound or is it just straight conversion?
Pretty straight conversion, like all the device drivers, such, all the navigation GUIs. Some of the main control software is still that legacy software, but for the most part, converting to ROS. UI isn't as operational, so we haven't made that jump yet, but hope to in the future.
So the umbilical cord for NUI, does that contain, I was interested in there's a compressor that's wrapped full of fiber optics, did I understand that? And then does that continue through the umbilical cord all the way to the vehicle?
And if you go back to the picture. Yeah, here, so we have just a CCD cable usually we can use to the depressor, which we deploy. Tether comes out of there, so that takes all the heat motion from the surface. This pretty much sits at 50 meters under the ship throughout the dive. There's also some acoustic modems in there, so we can speak from the depressor to the vehicle. Yep, so that's the unarmored tether. And then this tow body has the other spool, which are these guys here. And then there's sort of that tougher umbilical that can take more strain. That's connected to the vehicle directly.
What is the method of deploying and retracting line?
So usually in the Arctic, there's not much of a sea state. So usually we do depressor first, get that down to 50 meters, and deploy the vehicle. On Nautilus, it was a bit of a learning curve since we were in bigger sea states, and just with the crane of the ship, there was some sort of choreography that we had to figure out. But by the end, we got it down to a science where we would deploy the depressor to the surface, then get the vehicle in the water, then send the depressor down at the same time as the vehicle, so we keep the strain low, the tension low. And then once we hit that 50-meter mark, this tow body comes out, and that's when the vehicle descends.